Does a moving bumper car carry a force? The answer to that question is no. The moving bumper car carries momentum, but it cannot carry a force. A force is exerted by one object on another object, so a single object can't carry a force. But we intuit that a moving bumper car carries some physical quantity of motion with it, some capacity to make other objects move in the direction of its motion. That physical quantity of motion does exist, and the bumper car is indeed carrying it as it moves. That physical quantity is called momentum, and momentum is the conserved quantity of moving. As required of any conserved quantity, momentum cannot be created or destroyed, but it can be transferred between objects. So when I bump these two bumper cars into one another, they transfer some of their momentum. And you can almost see that. If I make one of them move and hit the other, one stops, the other goes. They're transferring momentum. Now, momentum differs from energy, another conserved quantity that we've already encountered, in a number of crucial ways, two of them in particular. First, unlike energy, I got to stop these guys before they get out of control. First, unlike energy, momentum cannot be stored. There's no such thing as potential momentum. Potential energy exists because energy isn't about moving, it's about doing. So moving objects have kinetic energy, but even a stationary object can have potential energy. Right now, the bumper car has gravitational potential energy. Momentum, however, is really about moving. So without motion, there's no momentum. A moving object has momentum, a stationary object does not. Or to be more technically accurate, a stationary object has zero momentum. The second way in which momentum differs from energy is that momentum is a vector quantity. It has a direction. To show you this, along with the fact that momentum is truly conserved, I need more room. So here I am in a bigger venue, a classroom, and I have a wheeled cart. It's kind of like a skateboard for real beginners like me. And I need the wheeled cart because friction tends to give away my momentum to the earth. And I don't need that. I mean, as it is, air resistance, there are many ways in which my momentum can leak out of me, not because I'm destroying it, but because I'm giving it away. So the wheeled cart makes that effect relatively small. I can show you momentum going in and out of me. Back in the lab, I use air cushions to move around the objects without letting them retain their momentum. Here, it's wheels. So, to start with, I have no momentum. And because momentum's conserved, unless something gives me momentum, I'm never going to move. I need to get me some momentum. And where I'm going to get it from is the wall. I'm going to have the wall give me momentum to the right. Momentum has a direction. It's a vector quantity. So the wall is going to give me momentum to the right. Now that will cost the wall. The wall will be giving up momentum to the right, which is actually meaning that it ends up with momentum to the left. We'll deal with that a little bit later on. But imagine right now, when I push on the wall, we'll talk about how the transfer occurs later in the next video. I'm going to have the wall push on me, give me momentum to your right, and I'm going to carry it with me. Are you ready? Here we go. I have momentum. I can't stop until I give my momentum away. When I got over to this wall, I gave it my rightward momentum and came to a stop. That's great. Now I can do the reverse. But now, this time, I don't want the wall to give me rightward momentum. I want the wall to give me leftward momentum. Here we go. I'm going to push on the wall's going to push on me. It's going to give me a nice dose of leftward momentum, and I've got it. I can't stop, I can't stop, I can't stop until I give it away again. So I can do this all day. It's kind of fun and a little dangerous, but not too bad. Off I go. I'm carrying it back and forth. And each time I do this, I'm exchanging momentum with the wall and therefore the whole earth, carrying whatever I end up with me. and eventually giving it back to the wall and the whole earth. Let's start that again, but now I want to have you watch when I encounter the wall on the right. So I'm going to obtain rightward momentum. I'm going to head toward the wall on your right, and when I get there, I'm going to do two transfers of momentum in sequence. Here we go. First, I'm going to get the momentum to the right out of the wall. I've got it. I'm carrying it with me. I give it all to the wall, and then I give more momentum to the right to the wall, and that costs me. I end up missing momentum to the right, which is to say, I have momentum to the left. A negative amount of momentum to the right is momentum to the left. And so when I encounter that wall on the right, I'm going to do it again. I can do this over and over, as long as I don't get injured. Off I go. I'm going to give it my rightward momentum and extra rightward momentum. I gave it more rightward momentum than I had. And I ended up with a deficit of rightward momentum, less than zero rightward momentum, which is to say, leftward momentum. That's what you do when you bounce off something. Assuming you bounce, you might want to bounce something other than yourself off of a wall, unless you're a small child having a lot of fun and are bouncing off walls. So when I encounter that wall and I give it more rightward momentum than I ever had, here it goes. I'm going to give it all my rightward momentum and extra. I end up with leftward momentum until I give it away to the wall again. As you can see, in order to go from having momentum to the right to momentum to the left, I have to make a huge exchange of momentum with something else. It's not something, I can't just simply turn my momentum around. Rightward momentum and leftward momentum are very different. And therefore, when I'm heading to your right, I can't simply turn around and head to the left without help. I need some other object, like this wall, to exchange momentum with in order to reverse my direction of travel. And that's one of the reasons why objects that are all by themselves just keep going in a straight line at a steady pace. This is Newton's first law of motion again, but with a more sophisticated twist on it. One way of looking at why objects that are left to themselves keep going at a constant velocity is they have a certain momentum, and without help, they can't change their momentum, and they have to keep going. Well, for me here on this cart, when I'm out in the middle of the room, I have to carry my momentum with me. I've got no choice. But in a bumper car arena, there are lots of other objects around with which to exchange momentum. And that's part of the fun of bumper cars. So we'll go back to the lab and start playing with bumper cars. So here we are back in the lab. I'm going to save the exchanges of momentum between bumper cars for the next video and concentrate for now on the momentum of a single bumper car. So here we are, bumper car solitaire. It's boring, but it's instructive. You can think of momentum as the currency of motion, and the momentum of our lone bumper car reflects how much of that currency had to be invested into the bumper car to bring it from rest to its current motion. It turns out that a bumper car's momentum, like that of any object, depends on only two things: its mass and its velocity. Let's start with mass. Momentum is proportional to mass, and I can show you a simple reason why that should be true. Let's start with one bumper car that's moving. It has a certain momentum, in this case, to the right. If I take a second identical bumper car and make it move exactly like the first bumper car, then it has the same momentum, again, to the right in that case. Well, suppose that these two bumper cars are being driven by people who are friends and they hold hands. Doing that turns this pair of bumper cars into one single larger bumper car. And if we get it moving exactly as it was before, it's now a single bumper car with twice the momentum of each bumper car individually. All I've done then is double the mass of a bumper car, and I've evidently doubled the momentum of the bumper car as well. Well, this is a typical physicist analysis where you look at this situation, the two cars by themselves, each one has one portion of momentum, and when you do something that has essentially no effect on the situation, you just have the people just touch hands, they become a single bumper car with twice the mass and twice the momentum. That analysis is a typical one a physicist would do. But the bottom line is quite important. The momentum an object has is proportional to its mass. It turns out that a bumper car's momentum is also proportional to its velocity. To start with, momentum and velocity have the same direction. But even the amount of the bumper car's momentum is proportional to the amount of its velocity. To see that momentum should be proportional to velocity, I'll put away the double bumper car and bring out two bumper cars that have Velcro bumpers. These bumper cars don't bounce off one another when they hit, they stick. And now I will give a usual portion of rightward momentum to the first bumper car and let it collide with a motionless second identical bumper car. When that collision occurs, the first bumper car will have to share its momentum with the second identical bumper car. What will happen to the velocity of the first bumper car when it's got half the momentum it started with? Its velocity drops by a factor of 2. It travels only with half its original velocity. So decreasing the momentum of the first bumper car by a factor of 2 decreases its velocity by a factor of 2. Showing that it's exactly a factor of 2 requires a calculation that I won't do. But it's really that's really the case. The momentum really does drop by a factor of 2. So overall then, the momentum of a bumper car is proportional to its velocity. Combining these two observations then, the momentum of a bumper car is equal to its mass times its velocity. That relationship gives us some interesting insight into what happens with bumper cars. Let me turn these guys off. The vehicles themselves have relatively little mass, so the riders contribute significantly to the total mass of a bumper car, and thus to its total momentum. The bumper car's behavior changes depending on who's riding in the car. When the only rider in a bumper car is a little child, the car carries relatively little momentum. As we'll see in the next video, when I start crashing bumper cars into one another, the low-mass cars can't transfer much momentum to whatever they hit and don't affect other cars very much. In the world of a bumper car arena then, the cars with the little kids in them are like bugs zipping around a lawn party. You barely notice when they hit you. At the other extreme is a bumper car that's carrying a couple of couch potatoes. I'm thinking in terms of really big people. And a car that's filled with really big people has a truly enormous mass. That car carries considerable momentum even when it's moving slowly, and it can transfer large amounts of momentum to whatever it hits. Its effects on other cars then are substantial. It's like a big hammer in a box of nails, or a bowling ball in an alley full of little bowling pins. It knocks everything for a loop. So how about velocity issues? What insights can we gather from the fact that momentum is proportional to velocity? Well, the faster a bumper car is moving, the more momentum it carries. Carrying a huge momentum is fine, but huge transfers of momentum can be a problem. In fact, even dangerous. So think about dropping a melon off a tall building. Near the bottom of its fall, the melon has an enormous downward momentum. And that alone isn't a problem for the melon. Hey, says the melon, wow, this is kind of cool. The whole world is rushing up at me really fast. It's not the fall that's the problem. It's the ground. When the melon reaches the ground, it transfers its enormous momentum to the ground. And the melon stops having fun. So to avoid the melon's fate and all the associated lawsuits, The people who run bumper car arenas limit the speeds of bumper cars. So bumper cars are supposed to be fun and exciting, not death-defying. So the masses of the cars themselves are small. Everybody who sits in the cars then has a big influence on the car's mass and therefore the momentum the car carries with it. The velocity of the car, well, the faster it's going, the more momentum it's carrying in the direction of the velocity. But they limit that maximum amount so that you're not transferring too huge amounts of momentum when you collide with things. So now for a question, one that's easiest to answer if you think in terms of momentum. Suppose your spaceship is coasting forward through empty space at constant velocity. You decide to get rid of the trash by throwing it backward out behind the ship. In other words, you give the trash backward momentum. What effect, if any, does that action have on your ship's velocity? By throwing the trash out backward, you're giving the trash backward momentum. You have less backward momentum as a result. You've given it away, and it's a conserved quantity, so you have less backward momentum, which is equivalent to more forward momentum, because a negative amount of backward momentum is a positive amount of forward momentum. So the remaining ship, you included, have more forward momentum than your ship had before. It also has less mass than it had before. So with more forward momentum in less mass, you're traveling at a greater forward velocity. So the ship is traveling faster. This whole process of throwing stuff out the back is how a rocket engine works. Now, you threw trash out the back and you're possibly in trouble with the galactic police. But if you throw gases out the back, as you would with a rocket engine, you're not going to get arrested and you're going to propel the ship forward at greater velocity. The act of throwing gases out the back of the ship at great speed causes them to carry away backward momentum and leaves the ship with additional forward momentum. And so it picks up forward velocity. That is how rocket engines work, as we'll see in the episode on rockets. At this point, you could picture a bumper car arena as filled with vehicles, each carrying its own momentum equal to its mass times its velocity. The stage is set for big things to happen, but that's going to require collisions, which is the subject of the next video.